So my name is Simon Perkins, and I work for the South African Radio Astronomy Observatory. And I'm going to be talking about Dask and radio astronomy storage formats. So yeah, just for anyone who's not familiar with the field, radio telescopes observe signals at multiple antenna pairs.
Simon, we can see your timer.
Oh geez, am I sharing the wrong thing? Oh. Okay, can you see the main thing, or can you see the notes too? Okay. So my name is Simon Perkins. I'm from the South African Radio Astronomy Observatory, and I'm going to be talking about Dask and radio astronomy storage formats. So radio telescopes observe signal along multiple antenna pairs called baselines, but they also observe along multiple time steps and channels, and this gives us a very large space of values. And the more we increase the number of time steps, antenna, and channels on our new instruments, the better quality images we have. So this is an example of the galactic center taken by Meerkat, which is the core of what will be the greater square kilometer array. Now the thing about this is, like, obviously the amount of data is increasing, and therefore we have increasing requirements for being able to process this increasing quantity of data. So I think all of us are now starting to use Dask X-array and X-array now. So SARAO, NRAO and SKAO, we are all sort of focusing efforts on developing with Dask and X-array. So I think, I think there are very compelling reasons to use Dask, especially with regard to the horizontal scaling, which I think is well discussed in the rest of this workshop. So I wanted to sort of ignore that for now and focus on data formats, which is an area quite close to my heart. So I think if I can just cover the area quickly, thus far in the 70s, we had the APES framework, which was associated with the FITS and UV FITS format, and the APES memo specifying the data representation. And obviously in the 90s and 2000s, we had CASA, which had the CASA table data system, which to me as a computer scientist looks like a columnar data storage format with C++ and Python interfaces and a SQL dialect. And I think what's impressive about this is when you consider things like Apache Arrow started in about 2015 and is now starting to sort of present the same sort of functionality. And obviously, CASA was associated, the specification for data there was the measurement set version 2.0. I would say the only downside to these frameworks is that essentially the formats weren't really designed for distributed, or the frameworks and the formats were never designed for distributed processing. I mean, distributed and cloud computing hadn't really taken off at that point. So now we've got to a point where the data volumes are just taking off. We need to scale horizontally to process them. And I think we're all heading towards Dask. The one thing that I want to point out is that in my opinion, the data access layers of these frameworks and formats are very tightly coupled. So if you're using CASA, you have to use the measurement set, for example. So yeah, I think we're now in a regime when the implementation changes, we're going to have to change our formats. And I think we've all been, you know, I think CASA NGI has been looking at SAR, and so we've also been looking at Parquet. I just want to talk briefly about Dask MS, which is our data access layer. And really the idea is that it exposes columnar radio astronomy data as X-array, as Dask arrays wrapped in X-array data sets. And I think this kind of format will look familiar to most radio astronomers. But I think the important thing about this is that, or the important thing about Dask that I want to mention, apart from its horizontal scaling abilities, is its ability to act as an interface. So we have many data sources available here at the top, such as the raw archive data from the telescopes themselves. We've got CASA-Core, obviously, as a format. Now we're looking at things like SAR, and I'm particularly interested in the ARROW ecosystem, where they're systems, where they're formats like ORC, Parquet, and the Hive, Apache Hive database. And then you've got data engines like Blazing SQL, Data Fusion. Now, and then now at SARAO, what we're doing is we're developing Dask applications like Cortical, Regavi, ShadeMS, and obviously the SDP pipelines. The SARAO SDP are developing their own pipelines via CatDAO. But the really nice thing about putting Dask in the middle, Dask MS in the middle as an interface, is that your applications then become abstracted from your formats. And that means that I think we can start future-proofing our applications from when the formats may change in future. So Dask MS can very simply convert between all these different forms, like SAR, Parquet, and CASA on the command line. We can also do it in the Python interface, and you'll notice that we're just going between data sets when we're doing an XDS from MS and an XDS to Parquet. So I've got a couple of strong opinions that I want to state. I think we really should stick to the measurement set version 2 and 3 specifications, because it's the lingua franca of our software, and we understand the specification quite well already. I strongly feel that X-array data sets should be the interface between our formats and applications. And I think we should, it would be really good to settle on something acceptable to everyone there. And finally, I want to say that the Apache ARROW ecosystem has many advantages as a format, because it's ubiquitous, high performance, self-describing with rugged data support, extensive language support, strong institutional support, GPU support, which future radio astronomy processing is heavily predicated on. So you've got things like the Blazing SQL GPU storage engine, which uses ARROW, the NVIDIA Rapids CUDA data frame and associated libraries. And then on top of that, you've got query engine support, which would act as a tackle replacement. So I'm going to stop there. Thanks for listening.
Perfect. Thank you, Simon. We're going to hold off for questions towards the end. Next up, we have Landman Beste, also from the South African Radio Astronomy Observatory. And Landman will be talking about distributing the W gritter for wideband imaging. So please go ahead.
Right. Hi, everyone. So this is some work I've been doing with some fellow SARAOians, Simon and John, who you'll hear from later, and Philip and Martin, who are at the Max Planck Institute for Astrophysics in Garching, are actually the authors of the W gritter. And I guess I should start by explaining what gridding is. I'll try to keep it simple, but unfortunately I need this one slide of math. If it's going to intimidate you, please look away. It's not important to understand anything, really. I just want to illustrate what gridding is. So radio interferometer, we know responds to an image of the sky according to this relationship, right? And it would be a 2D Fourier transform were it not for this W term over here. Anyway, the integral can be discretized and we end up with a linear model of this form. And essentially what gridding and degridding is, it's efficiently evaluating this measurement operator, which typically maps an image cube, so of a number of pixels and a number of imaging bands, into a set of complex visibilities with a certain number of channels and then a certain number of rows. And generally we have that the size of the image is much less than or much smaller than the size of the data. So this can be done, so gridding and degridding can be implemented efficiently using a combination of the non-uniform FFT and W stacking. So in a nutshell, what that is, non-uniform FFT, what we usually do is we take our data and you convolve it with some convolution kernel onto a regular grid. You take a Fourier transform and then you have some detapering function to reconstruct the signal. When things are not, well, when you've got a W term, you can deal with this by binning in W, and so you end up with a number of W stacks. So you've got a number of Fourier grids, and then you just grid, you bin in W and you grid the different W bins to different Fourier grids, you FFT them all, and then you've got a modified W screen that you have to apply, which is different for all the W stacks. You combine them, you get something which is called the dirty image. That's basically our data projected into image space. Now the complexity of this operation, essentially it's the number of data points multiplied by the support of your gridding kernel, right? And add to that also the complexity of the FFT, right? Multiplied by the number of W stacks that you have. So that's really it. All of these details are obfuscated from us if we invest in the W gridder, which does most of that for us, and it does it in a very smart way. So you can read more about the W gridder if you follow the link at the top here. Essentially, it uses an improved form of W stacking, which grids in 3 dimensions to minimize the number of W layers required for specific accuracy. And then it also uses what's called the exponential of a semicircle kernel. And the advantage of using this kernel is that it's very quickly to evaluate. And so you can evaluate it it's very cheap to evaluate. So you can evaluate it on the fly and you don't have to tabulate it and then use lookup tables. So this is actually the key to the accuracy of this gridder. And what these guys did is they implemented it very efficiently in C++, gave it some PyBind 11 wrappers, and this is available in the Duck package, which also has a number of other bells and whistles. I'll mention the FFTs that are implemented in Duck. That's the algorithms used by NumPy and SciPy at the moment. So all of that translates to a very efficient, lightweight, and almost arbitrarily accurate wide-field gridder that has a Python interface. I say almost here because you can get to about 10 to the minus 12 with respect to the direct Fourier transform. And the question is, how do we turn it into a practical wideband gridder? So to explain that, I need to tell you what features it has and what features it doesn't. So in its sort of vanilla form, the interface for the Duck gridder does multi-frequency synthesis gridding and degridding. And what that means is that it only deals with one imaging band at a time. It doesn't deal with image cubes, right? So it assumes that you've got one imaging band, which maps then to a number of visibility channels and rows. So we actually have to go, if we want to do image cubes, and implement the visibility channel to imaging band mapping ourselves. It also has internal parallelization with a very low memory overhead. In particular, the memory usage does not scale with the number of W stacks. And then it interfaces with NumPy arrays. So this is assumed to be kept in memory. And if we want to do out-of-memory compute, we have to chunk it up ourselves and then interface it with common radio interferometry data structures, such as measurement sets. Importantly, all the padding, oversampling, and W-tone corrections required for specific accuracy are handled internally. And this turns out to be both sort of a pro and a con, as I'll explain, because we don't have access to the intermediate grids. It also doesn't know anything about polarization. So interferometers actually measure a polarized signal, and we end up measuring something called a correlation, and we have to transform that into the physical quantities of interest known as Stokes parameters. And it doesn't scale horizontally, right? The parallelization is internal, and it's for one imaging band alone. So what I'm going to try and convince you of is that all these latter things can be handled very transparently by Dask. And the first step to doing that is to write our chunk Dask wrappers. These are available in the Codex Africanus package. I've put a link to the documentation down here. And the idea is essentially for chunking over the frequency axis that the number of imaging bands determines your channel to band mapping. So for example, if you have 8 imaging bands with 4,000 visibility channels, then you end up with 500 channels in every band. And then because every imaging band is treated independently, it's quite natural to chunk over band, which then translates to a chunking over channel. In addition, since the measurement operator is linear, we can in principle chunk arbitrarily over row, but if we do this naively, it introduces overhead because our W stacks are, the number of W stacks required depends on the spread in W values. And so if you just take your rows and split them into 2, for example, you have the same spread in W, and hence you're duplicating the number of FFTs that you need to do. Anyway, once you've got your chunked wrappers, we have to interface it with some data structure. And the way I've done this in PFP Clean, which is actually an imaging and deconvolution package I'm working on, is to interface with measurement set-like structures. And usually the first step in my workflow is convert a measurement set to either ZAR or Parquet format, which is then chunked on disk, and therefore can be read and written to much more efficiently. To deal with the distribution and parallelism, we have to specify these specific parameters. Host address tells you where your cluster is, and so you can connect the distributed client. If it's not specified, we'll just default to using a local cluster. The number of workers, well, this we default to the number of imaging bands. A memory limit is used to try and avoid memory spilling to disk, so it will try to chunk things cleverly. The number of threads needs to be specified that you have available on each node. And you also have to spec the number of threads per worker. Importantly, this is the number of Dask threads that you want to run on a node. And then the number of threads that you give to the gridder is essentially the total number of threads that you have available divided by the chunks on a node. And this allows for both horizontal and vertical scaling that I think is probably best illustrated with an example. So here I've taken a typical Meerkat measurement set. It's an 8 hours observation with 8-second dump rate. It's about 5 million rows, 1,000 channels for correlations. And I'm creating a 3-degree by 3-degree dirty image sampled at twice the Nyquist rate with 8 imaging bands. And so I get an image size of about this size. The PSF is twice that size. And I fix the gridding precision to about 10 to the minus 5. So the first example here, if we just allow for vertical scaling, so here I'm basically setting my number of workers to 1. I've got a lot of memory in this case. I don't worry about fitting things into memory. And I say that 64 threads, and I've only got 1 Dask worker. So I give all those threads to the gridder. And what this means is that I'm sequentially stepping through imaging band. And what you see here, blue is basically reading from disk. The green is the work that the gridder is doing. And you see that actually the I/O is completely dominating here. It takes about 500 seconds. So then we can start scaling horizontally on a local cluster. So here I've given it 8 workers, which means that now we're doing all bands in parallel and each gridder only gets 8 threads. This helps a little bit, but you still see that I/O dominates. We take that a bit further. Obviously in the last case, there's eight times memory overhead. We keep scaling like this, the memory overhead gets better, and eventually we get to a point where, okay, the memory overhead is much larger, but we're no longer increasing in performance. And that's basically because we get limited by I/O. We can't read fast enough, and also as we chunk, we introduce overhead in the gritter. So for this problem, we really want to scale onto a cluster. And so here I've just done an example where I've run it on a PBS cluster at the South African CHPC with 8 workers. Each one has about 120 gigs of memory, 24 threads, and I've said 4 threads per worker. That means each gritter gets about 6 threads, and we see we approximately half the computing time. So that's about it. It works. I hope I've convinced you that the ability to scale both horizontally and vertically is crucial to make optimal use of our resources. The distribution strategy needs to be flexible and transparent to the user. Fast storage formats becoming increasingly important. Critical, as Simon said, to have a common data format. And then also there are many things that can still be improved, like, for example, binning row chunks in W, better memory budgeting, many unresolved issues, but lots of progress being made. So thanks, I'll stop there. If you would like to get involved, email me. Package is public, release is still pending. Thanks.
All right, thank you. We can take questions at the end. Next up, we have Lexy Andati, who is also from the South African Radio Astronomy Observatory.
Yes, can you hear me?
Yes.
Okay. So my name is Lexy Andati, and today I will be speaking about RAGAVI, which is a Radio Astronomy Gains and Visibilities Inspector. First of all, I'd like to say it's an honor for me to be here to interact with people who I only see on YouTube videos and Twitter. So who am I? Allow me to introduce myself before I begin. My name is Lexy. I am a postgraduate student at Rooyen University, and I am from Kenya, and I currently work with radio interferometric data. And my work is basically to try and build tools around this data to ease the life of astronomers. So a bit of context on what I'm about to speak on. In radio astronomy, we use radio signals from the sky, which come from astrophysical objects, for example, galaxies, and we try to image those objects and study them. So the way we capture the signals is by using radio telescopes, for example, the meerkat, which is shown in this image in this slide. And the radio telescope does this by sampling the signal at some interval and storing the data in some radio astronomical data storage format, some of which Simon has already spoken about. But because of the atmosphere and instruments and destination, nature of instruments and other factors, the radio signals that are captured have various corruptions. And for astronomers to be able to use the data captured by our radio telescopes, then this data must be freed from the corruptions. And we call the process of removing the corruptions from the recorded data, we call that process calibration. So in calibration, we try and get solutions which can be applied to the corrupted data to form corrected data, which will allow astronomers to image whatever they get from the telescope. And these solutions are known as calibration solutions or gains. So the corrected visibilities here is what I'm calling the corrected data, is what astronomers usually image. And they end up with such beautiful images that we might have seen around before. This is an image from, an example of an image from a galaxy from one of our colleagues in the research group. So the process as I've described it is I've oversimplified it, it can be a very lengthy process, and it's sometimes repetitive and sometimes complicated. But before we get to such beautiful galactic images or images of the sky, it is important to check the quality of the visibilities before and after calibration. And it's also important for us to check the quality of the solutions before they apply to the corrected visibilities. Sorry, before they apply to the corrupted visibilities. And the way we do that usually is by visualizing by plotting the gains. We plot the calibration solutions before they apply to the corrupted visibilities. We also plot the corrupted visibilities before the gains are applied to them and afterwards to see the quality of the effect of those solutions, if they are acceptable and if they do bring corrupted visibilities to an acceptable value. But visibility data can be quite large, as Landman has explained. For example, an hour's observation from the meerkat can generate almost a terabyte of data. So the problem that we were trying to solve with Ragavi was that we needed a way to generate portable and interactive plots for our data reduction pipelines, which are the pipelines that get us from the corrupted visibilities to our images. And also the plotting tools that were available at the beginning of this work, they took a really long time plotting visibilities. And there were sizes of data sets which these tools could not plot, and they had memory limits, so they could only plot these data sets if they are averaged down or reduced inside. And this is not always desirable, because a lot of information could be lost during averaging if you're not careful. And so Ragavi emerged. Ragavi is a Python-based tool that is run from the command line and produces interactive standalone plots. And to achieve this, it uses a combination of Bokeh, which is a well-known plotting library, Datashader, which is also another plotting library and very useful for large data sets, and Dask through Dask MS, which I think someone has spoken about. And Dask MS acts as the interface between our stored data and Dask for processing. So it's fairly easy to generate gain plots because they're generally small in size, and therefore they can be easily plotted using Bokeh without any modifications. And this meant that I could make the plots very interactive. For example, in the video I'm showing, I demonstrate the normal Bokeh interactivity. We can see that Bokeh provides some default interactive widgets such as panning, zooming, and such things. But I could also add some custom interactivity, which are the widgets above the plots here. The plots are not so important. This is just for demonstration purpose. And with those widgets above the plots, whoever is using this plot, whoever is interacting with this plot, is able to select what is visible and what is not, what is to be not visible in the plot. And they can also move around and change around items in the plot. This plot is a standalone plot. It just requires the browser, and so it can be it's very portable. It can be easily shared with peers for reviews and corrections and kind of things. Yeah. So, but for visibilities, it's a whole different ball game, because the data sets are almost always larger than memory. And for example, in the images I'm showing here, run a data set of about 55 gigabytes, which contained almost 1.72 billion data points on my computer, which has 16 gigabytes of memory. And it took about 14.5 minutes to process and plot. And this was because Dask was used in the processing, and it was possible to do this in memory, because without applying too much pressure on my memory because Dask and its mechanism enabled it to chunk and parallelize whatever was going on. Additionally, datashader, which also uses Dask data frames for plotting, was also used to generate the plots here. And luckily, because datashader and Dask work together well, we are able to end up with plots such as this. So this plot is a representation of my 1.72 billion points. And because datashader works very well with bokeh, integrates well with bokeh, we can also, I was also able to have the default bokeh interactions, as you may see at the top of the plot there. So in conclusion, Dask has played an integral role in the development of this tool, and that cannot be denied. But as much as it's currently possible to plot very large data sets on my laptop, there's still room for improvement. And I'm really happy that I got to attend this summit because of the great talks I have seen here, and I've learned a lot more about Dask optimization capabilities and gathered a kind of a deeper knowledge about where I can improve. And so I'd just like to thank the organizers of this summit and the developers of Dask for making such a great tool for us to use. Thank you.
Thank you, Lexy. Next up, we have Tim Cornwell from SKAO, and he will be talking about RASCAL, the Radio Astronomy Calibration and Imaging Library. Tim?
Yep.
Cool, thank you.
To share my screen.
Yep.
Yeah, I'm very pleased to be here and pleased to have this meeting and a chance to hear the great talks. Very interesting to the work that I've been doing. So I'm an unusual person. I'm a freelance radio interferometrist. And at the moment, I work for the Square Kilometre Array in the SIM team, and the SIM team works on simulations and pipeline processing of data. I want to not spend too much time talking about the Square Kilometre Array because probably you've heard of it, and there's also Google you can go to find out more about it, but it's going to be the world's largest radio telescope. So I'm just having a little bit of trouble here moving around my okay. So the amazing thing about SKA is the data rates, and everyone likes to say the data rates are very high. So there are terabits per second coming from the two different telescopes, one in South Africa, that's SKA-1 Mid, and one in Australia, it's a low frequency telescope. Signals go into a central processor which does correlation and beamforming where necessary, and then into science data processors. The connection there is still about 5 terabits per second. The processing that has to go on is about 250 petaflops. That's what it's specified at, and that gives a yearly rate of about 600 petabytes per year. So it's a very substantial telescope. The amount of processing that we have to do is very large, and we've been working. The community has been working on getting the ability to do that processing in a number of different ways. The part that the SIM team has been involved in is writing a library which is a library called RASCAL, which is used for simulations and for calibration and imaging. So you can find it on GitLab. It gets built every time we do a check-in into into Rascal, into the GitLab. The build time takes about 2 hours because it has a lot of processing to get. If you're interested and want to contribute, just send us a pull request, and we'd be very happy to look at it. The documentation is online and at that location. It's being developed as part of the square kilometre array effort, and it's the UK square kilometre array effort, and it's currently used in SKA simulations and as a possible use for SKA science data processing. The key aspects of the science data processing for SKA are a tiered execution environment, which provides data management and scalability. Obviously, scalability is a very important factor. Well-factored, reusable processing components, and those are as true functions used in directed acyclic graphs, so it matches well to Dask. Specialized high-performance computing components to exploit the node architecture. So you can have heterogeneous nodes with some with, for example, GPUs on the spot as needed, and scriptable workflows. The Rascal was started as an algorithm reference library, and we sort of decided it was more useful than it's just a reference library. And so it changed the name and the ambition a little bit more. The design is very straightforward and clean. Data are held in Python classes, and the classes correspond to familiar concepts in radio astronomy, things like visibility, gain table, image, configuration, so on. There are no methods attached to the data classes, and stateless standalone functions are used for all processing, which is a very nice simplification. Okay, so Dask, well, we adopted it in 2017. I ran across it, I can't remember where, and read the documentation, was impressed. We tried it out a bit. And this is the first check-in to our software, which was April the 25th of 2017. So it was still quite an early version at that point. We've tried to use Dask bags. In the end, we decided to use Dask delayed. Works very nicely. We've had problems using Dask with legacy software. In particular, we find things like threading errors. AstroPy is particularly vulnerable to that. But it's been a very good basis for development. I don't think that it's a straightforward way of thinking to build a graph and then execute it. And so we haven't actually seen a lot of developers adopting it. And more recently, we adopted Xarray, and we use it instead of NumPy for the low-level data classes. We haven't fully exploited Xarray yet, but we hope to do that. A lot of the things like looping through the data structures use Xarray capabilities. Sort of things we've done. These are all driven by the needs of the SKA development, so that we've had requests to do, for example, simulations of non-isoclimatic observations. So you set up a test sky as a collection of point sources, propagate the signal through the atmosphere, some overall sources to get the predicted visibility. You can self-calibrate to get one gain solution for the entire field, and then look at what's left over. And we've done a fair bit of that sort of work. And Dask works beautifully for this because it's a straightforwardly parallelizable problem. Here's an example where we had a double source But the question was, if you observe with the mid telescope, would the troposphere ever cause you non-isoplanatic problems? And yes, it does, but they're very weak. We've also done some work on simulating the effect of radio frequency interference, and this is looking at the effect of digital TV in Perth, which is 800 kilometers away, and at 170 megahertz. The image on the right-hand side is a full sky image pointed at the south celestial pole, and that collection of Fresnel light patterns correspond to the interference coming from the digital TV station. So we learned some interesting things from doing that. But let's talk mainly about the processing pipelines. These convert visibility data into images. We distribute over frequency using Dask, and distribution over time is done internally to functions. For example, a primary beam changing over time. We have three pipelines that we're interested in: a continuum imaging pipeline, the standard iterative calibration pipeline, which is ICAL, and that runs all the time on the telescope, so it has to be well understood and well engineered, and the spectral line imaging pipelines. So we've concentrated on the first two pipelines. ICAL is a very straightforward algorithm in which you jump backwards and forwards between image space and data space, making a prediction, adjusting the prediction of the visibility, adjusting the calibration, predicting an image from that, updating that image, and switching backwards and forwards. As I said, this is the workhorse algorithm, and it's kind of straightforward to do in Dask. This is the ICAL graph. So it started off on the left-hand side. I presume everyone who's had experience with Dask has seen these graphs. So there are 8 different frequencies being combined together, and it's gone through, it's in its second major cycle. So when we first started using Dask, it couldn't generate these graphs, and the fact we can do now is very welcome. The task stream is another interesting diagnostic that you can have. So this starts off on the left-hand side with grading visibility data, actually reading it in, and then starts off doing major cycles. And you can see there's a big bar where only one worker is doing any work, and that's because we haven't been doing any, we've been doing a deconvolution of the entire image. And this is a problem for optimization if you have an algorithm that doesn't exploit locality very well. So what we've done in this case is we've changed deconvolution to work on patches all at once, and then we reconcile them. And if you do that, you can get a much better task stream where you're losing some fraction of time, but the overall efficiency is sort of 60–70% now. Okay, so this is a typical simulated image. So we've been doing work with other SKA teams to compare our implementations of the continuum pipelines. This is a typical source. It's what sky looks like at 1.4 gigahertz observed with SKA mid, of which Meerkat is part. So this is an 8K by 8K image. Eventually, the requirements call for a 200K by 200K image, and that's going to require something entirely novel to make that work. So I just want to finish by talking about something that I've been doing recently, which is resource estimation. And this is really important because we use the pipeline to calibrate the telescope. So it runs all the time. So you have to know how much resources it needs so that a particular observation can be scheduled. So a model for the ICAO processing cost is essential for operations. Now in Raskil, nearly all of the processing is done using Dask. And so there's very little that isn't done using Dask. So what this means is we can use Dask diagnostics to track the time spent per function. And so what we do is we write the CLI arguments, the data info, the environment info, and the Dask statistics, which you can get at the end of a run to a JSON file, and then we just evaluate those. So I'm going to show you a few plots from that. There are about 30 control parameters for the algorithm, about 10 significant resource consumers functions that are run. So eventually we might want to build a model, but we've been able to understand what's going on so far, which I'll show you about. So this is just bar charts of the time per function. On the left-hand side, we show the total time per function. And on the right-hand side, we show the time per function call. And so the, we can look at the overall big consumers, and they are things to do with invert and predict. So those are transforms backwards and forwards from image space to data space. Interestingly, what we found is that we do a lot of scabbers in image space as part of the deconvolution, and that is taking a lot of time. We have to look into that in detail. I suspect it's something to do with the way we're using X-array or misusing X-array, and so I think we can probably get that down. But we're going to have to squeeze these curves as much as possible. The major part of the transforms between image space and data space are just due to are in the gridding algorithm that was mentioned before. We use the nifty gridder as we know it, so our next job is to try and reduce that. So we're developing a version of the nifty gridder that will run on a GPU. And sort of with this information, with this sort of diagnostic information, you start looking into, how the scaling occurs as a function of problem size, and the facilities you have available to do the processing. This shows you the time per function. In this case, the invert using nifty gridder versus image size and data size. And you can see that it actually scales quite nicely for large data sets and images, or understandably. So that's the scaling that we get for the top right-hand side of this diagram. So this is, once we go through and generate these, we can actually then just have a modified version of the imager, which will load the data and the command line arguments and just tell us how much processing it will take. So that's the ultimate goal. And yeah, I should say one more thing about this is just finding where you put your effort. To try and optimize, you have to understand where the time is going and improve it. So the larger context of our work is the SIM team is working with other SKA teams, such as in the Netherlands and in Australia, New Zealand, and hopefully soon the South African team again. And we're working on comparing continuum imaging pipelines, and matching their capabilities, comparing their capabilities. We're going to be moving suitable kernels to GPUs. We've already done DFTs, and that's been very much worthwhile. Certainly, we have to move away from legacy serial data formats. That's some urgency, and obviously that was a topic that we probably all agree on. And there's an ongoing process to scale up to larger data sets and image sizes. At the moment, we're just this cross-team effort is just working on data sets of 10 gigabytes because those are easy ones for people to download. But we're probably going to have to go up by another order of magnitude in the next steps. And then the other thing, which is an intrinsic part of the SKA architecture and science data processing vision, is that we do interoperability of components from other SKA packages using the best of breed, essentially. This is actually a pretty tall order to be able to do this, because it requires APIs to agree and data formats to agree. But it's a direction that we're going in. So, I mean, just to summarize, our experience using Dask has been very positive because we were early adopters. We've seen it improve immensely over the time that we've been engaged with it. And I'm just generally very impressed with the level of professionalism and also, interest in problems that the Dask team showed. So that's it. Thank you.
Thank you, Tim. Looks like we have a short break at this point. Sorry.
They moved that functionality to Duck.
Yeah. We're working from the Duck version.
Okay. And yeah, it's interesting to hear you guys are working on the GPU side of things. Specifically using the analytic kernel, I'm assuming. That same.
Yeah, that's right.
Okay.
Yeah, the same approach. So it's a collaboration between the NZAP team and the SIM team at the moment. And so the NZAP team has provided the kernels, and we in the SIM team, mainly Fred Dulwich, is doing the interfacing to Python. Yeah, cool. So I'm looking forward to seeing it.
Yeah.
I guess I have a question for you, Landman. In the task graphs you showed us, was task stealing turned off?
So actually what I showed, I didn't have time to go into too much detail here, but so this is all, if you allow for graph optimization and you just run the vanilla Dask scheduler, it doesn't come out looking like this at all.
Yeah, it looks exactly.
So this is very clean because I'm using a scheduler plugin that's actually been developed by, well, that Jonathan Kenyon that's giving his demo later we'll be talking about. And this kind of just makes sure that you minimize transfers. So the few transfers that you're seeing here are things like flag row being communicated across workers and autocorrelations. And also, I'm not cloning the UVW; those are just sent across the network to each worker. So, but yeah, it's so worker stealing, I think, is switched off. Yes.
Thank you.
I think there's a question in chat from Bruce. Tim, you mentioned you're moving away from formats like FITS. What image format are you using instead?
Another one. I don't think we've decided yet. We've looked at HDF, but the next thing we're going to do is look at ZAR, I think.
So the idea would still be to kind of keep the FITS data model in terms of WCS headers and all those things, and so it's, I guess, a similar sort of idea to what Simon had about keeping the measurement set data model, but just changing the storage backend.
Yeah, it's too painful to give up the WCS capabilities. So yeah.
So I confess I haven't looked at it myself, but I know the Carter project, its idea has a sort of HDF5 based format that's chunked in some way to support visualization.
Yeah, that's right. It uses HDF5 IDIA. And so, we're going to be looking at that as well. I mean, the fact that you can read it into Carter is of interest. But I mean, we just can't bear the cost of writing these, 10, 20 K-pixel images to FITS. It's just not feasible, not sustainable.
I guess also have a question about the Ragavi viewer. Is the visibility viewer seem to be showing a 2-dimensional plot? You normally have at least 3 dimensions if you've got sort of time, frequency, antenna 1, antenna 2 polarization. Does it support those kind of high dimensional views?
Not yet, but I think it's something that we may look into in the future development.
Okay, so what are you plotting at the moment? Is that just kind of an average over baselines?
No, it's just the data points as they are from the from the measurement set. So it's just a 2D plot.
Okay, so what it's row and frequency.
Yeah, for that specific plot that I showed, it was just time against amplitude for all the available channel, and basically it was just that.
But the axes are selectable, correct?
Yes, they are. They are.
Okay.
Jan-Willem Steeb from NRAO also. Jan, are you ready?
Yeah.
Great. And he'll be talking about Kasangi, Casa Next Generation Infrastructure.
Well, just CNGI.
Sorry.
It's fine. Okay, great. So I'm Jan-Willem Steeb. I work at the National Radio Astronomy Observatory in the United States. However, I am also a South African. I'm just across the pond from most of the people who gave talks earlier today. Okay, so just a bit of a recap of what the NRAO is planning and what's happened in the last couple of years. In 2015 to the 2020 strategic plan, because of all the developments in new telescopes that are being planned and being built, there was a mandate to look at modernizing CASA core to keep it up with the new processing demands. And then in the winter of 2019, we started looking at what technologies we could use to replace current CASA and CASA core. And we did a couple of trade studies, and we had a big basket of possible technologies and languages. And at the end of this process, we came to the answer of using X-ray and Dask. And what's great is that so many other people in the community have converged on the exact same answer independently. So it justifies the study in a sense. Now, we started prototyping in the fall of 2019, trying out a couple of different possible solutions for a storage format as well as a way of processing the data. And basically we came up with, we will be using the general layout of how the measurement set is defined, but with a couple of tweaks, which I'll explain later. Now, the NGCASA project and prototype is basically geared towards 3 telescopes and needs to be useful to all 3. So currently we have ALMA in Chile and the VLA in New Mexico, which are currently operational. So NGCASA should be able to do all the imaging cases that they need, as well as the NG-VLA, the next generation VLA, or I guess SKA North. So it is a complementary array, large array that will be built in the US. And yeah, hopefully it will be complementary to what is being done for the XKA in South Africa and in Australia. Okay, so here is how we divided the prototype package into sub-packages. So first we have CNGI, which is CASA next generation infrastructure. So this is loosely related to what is in the old CASA core. So it consists of conversions, so converting from legacy formats like the measurement set, and it doesn't currently have that capability, but in the future to convert from the ASTM, which some telescopes produce, or from FITS files. DI, that is basically opening up our data formats on disk, which I'll describe later. And then we have viz and image. So viz is basically all the functions that do operation on visibility data, so on data from the measurement set effectively, and then image on images, and then direct, that's basically some modifications we've done to the parallel processing framework. So that's functions related to Dask. Now, NGCASA, that's where more the bigger CASA-like functions, I guess equivalent to what you would call tasks in CASA are. So that consists of flagging, calibration, imaging, and deconvolution. Now, it should be noted that there will be another layer on top of this, which is the application layer. So the application layer is what astronomers and pipeline developers will interact with, which will contain all of this lower level functionality. So when I show a demonstration, you might say, oh, this is a bit tedious because there's a lot of settings and things you need to do. And the reason for that, this is a lower level interface. Okay. Now, for this project, we spent a lot of time specifically focusing on imaging because that is generally where the bottleneck is. It's been mentioned, I think, 3 or 4 times already about the computational complexity that happens during the gridding step. So where we take our visibilities and we smear them out on a UV grid. That's usually where most of the compute is. Okay, so here I'm just going to quickly show what's in current CASA and in NGCASA and how we've changed things up. So CASA core supplied a lot of data structures, arrays, there's viz buffers, image stores, and things like that. In NGCASA, we're using NumPy arrays, Dask array, and X array. Then CASA core measures, that is where we do all the transformations from pixels to coordinates and transforming from different reference frames, all of that. We're moving to AstroPy. MPI OpenMP, Dask distributed, C++ and Fortran to NumPy number. So I think there might be other cases, but we've actually implemented our gridder in Python. It's not written in C++ or Fortran like some of the other gridders that then are wrapped in Python. Ours is written in, written in C++. Ours is written in Python and then just in time compiled using NumPy. And then, of course, this is the everyone's talking about, and that's using GPUs. We haven't yet started on that, but that is on our timetable to also do GPU gridding and also look at things like TensorFlow. And then the measurement set, CASA images and so forth, we've got our new formats, which I'll discuss. Now, just to have a top level overview of the prototype infrastructure. So first we'll start with our storage solution. We wanted it to be both local and on the cloud. We want it chunked in n-dimensional arrays so that we can read one chunk at a time, because if our data is larger than memory, which can be the case, we want to be able to process a chunk at a time. So we decided on ZAR for serialization and compression. And because it's cloud optimized already, and it has support for complex numbers. Okay, then the actual processing will start in the centermost rectangle. So our code acceleration, a number for accelerating all of those Python for loops, NumPy for vectorized operation, and then CuPy is aspirational GPUs. We would like to do that. And then our data structure, X-ray, Dask for parallelism, and then AstroPy for all of those conversions. And then we also have Kubernetes and Docker to allow us to deploy on the clouds like AWS. Okay, and then user interaction of it, of course, you can interact with it just using a simple script, but also with Jupyter notebooks and the Bokeh dashboard. Okay, so these are the ngCasa data formats, and some of them aren't yet rigorously defined or spec'd, but I guess the important ones are the measurement set equivalent, which is viz.zar. So it's based on the MSV3 definition with a couple of tweaks, which I'll get into. Images is image.zar, and then we have a couple of other more niche formats, data formats as well. Okay, so I guess the big thing is understanding that at the end of the day, it's basically n-dimensional chunked arrays, and these are all just NumPy arrays once it gets into memory. But if we start on the right with my Russian doll example, we've got ZAR, which is on disk, and then when the ZAR chunk is loaded into memory, it's a NumPy array, but we delay it by using a Dask array, okay? And then that is stored within a X-ray data array, which gives it labeling. And then an X-ray data set is a collection of X-ray data arrays. And then we've added another layer on top, and that is a collection of X-ray data sets, which is a multi data set. Okay, so I'm going to show a simplified example of the viz.zar, the viz XDS, okay? And this is just using X-array. So first we have our dimensions, then we have our coordinates. Now, if you look at our coordinates, those with a star are what we call the dimension coordinates and are related to the dimensions. And this is what is used to define the dimensionality of our data. So here we have our data variables, and you can see each one of them has dimensionality specified by the dimensions. Now, this is one of the departures from the MS definition. Instead of having the row, we've split the row into a time and baseline dimension. So if you want a certain baseline, you can just index into that. You don't need to go through the rows and find a specific baseline you want. Also, we've changed the weight data variable, or the weight column, to be equivalent to the weight spectrum. So it has full dimensionality as the actual visibility data. Okay, so there is no more traditional weight column in that sense. Okay, and all of the data variables, when you open it, it's lazy, so they're all Dask arrays. So it's basically just one big dictionary, because it's not loaded into memory. Okay, now this is also a slight departure from the MS. So the coordinates, those are fixed defined names. They cannot change. However, we allow the data variable names to have names whatever you want, okay? Now, the names I've got there are what we call the default names. So for example, data, UVW, and whatever. But during the processing operations, we can add data variable names which aren't non-default. For example, if I want to do a phase rotation of my data so that it points to different phase center, then I can add data rot and UVW rot. Okay, so that has transformed those data variables. Okay. Cool. Now, there is a bit of a problem in that it's not an ideal world, and sometimes you have missing baselines. Either a telescope stops working for, a dish stops working for a certain amount of time, or the source, something obscures it, or so forth. So then sometimes we have missing baselines. Now, because we split the baseline and time axes, that basically leads us to sometimes do some padding with nans. So if there's a missing baseline, it's padded with nans. However, in the case where the baselines don't agree at all, then we can create separate XDSs. Okay, so we don't need to just pad everything with nans. Now, what I showed first was what we call the XDS. So that's a single data set, but then we have a data set of data sets. Now here again, we have dimensions and data variables. We're reusing the X-ray data set, and we basically in the attribute section, that's where we put all the dictionaries that are for each one of the XDSs. So this represents our visibility data. Then we also include all the subtables in all the MA. So this is all the meta information that's needed for some imaging processes. For example, the field and the source tables are all here. So the XDSs have consistent dimensions, and then all the metadata that is related to each one of those XDSs is also stored there. Right. Okay. Now, chunking the data is a core pillar of the CNGI and NG-CASA, and we have two levels of chunking because some algorithms prefer chunking on one axis versus another. For example, if you're doing a calibration, doing a self-calibration, you most probably want parallelism over the time axis. However, when you're doing a large image cube, you want parallelism over a channel. So what we do is we have a fine chunking on disk in ZAR, and then we have a coarser chunking, the Dask chunking, which is a multiple of the ZAR chunking. Okay, so when you call read viz, you can send it the chunks you want. So you can say, this is the number of channels in a chunk, the number of baselines in a chunk, and so forth, depending on the algorithm you want to do. And of course, all of these compression algorithms are supported, and that's given to us by ZAR that uses num codecs. Okay, so of course, most radio astronomy data is stored in the measurement set, so we need to be able to allow to convert it. So if you look here, we have the describe MS function that will basically tell you what's the dimensionality of the data in it. Now, when a conversion happens, to keep that dimensional consistency, it will split out each one of the spectral windows in a separate XDS. Okay, so in this example, we have 4 DDIs. Okay, so that's a combination of polarization and spectral window setup. And at the end, when you do the conversion, you will get 4 XDSs. Okay, and then here is example using the convert MS function, where we've selected we want DDIs 0 and 2, and then that will get converted. Of course, you can also specify the chunking shape you want for the data that gets produced. Okay, now that was for viz.zar, but now we also have an image format. I think during the break, something like that was mentioned as well. So we have it's ZAR on disk again, and then we have an X-ray data set. Now, it's pretty similar to how the images defined in CASA. However, there are a couple of tweaks. So for example, we've added the time dimension, and the time and channel dimension can be changed from time and channel to become Taylor terms that describe that basically have a function that describe the variation over time and channel. So that's also possible. Again, this is simplified. I don't list all the information, but it should have all the information so that you can do all the world coordinate system library transformations. Okay, so now we move on to Dask. Okay, I'm not going to, I think a lot has been said about building graphs and things like that, but there are different ways to interact with Dask. We basically use the first three. Okay, so we use built-in Dask functions. For example, we use the Fourier transform functionality to transform gridded visibilities into dirty images. We also use map blocks in a lot of functions, and then also custom Dask delayed functions. So the gridder actually makes use of Dask delayed objects. So we have our number gridder, and then we wrap that in Dask delayed, and then we feed it all the chunks of visibilities. Cool. Now, I think I just want to show an example. Okay, did I share it correctly? Can everyone see the Jupyter notebook?
Yes.
Okay, great. Okay, so again, it's a simple pip install CNGI prototype, and the data, we've got about 5 imaging notebooks showing different cases of imaging, and the data can be downloaded from our Google Cloud account. So here I'm opening my simulated Mosaic data set, and I'm printing out the MXDS. As you can see in this case, because it's simple and simulated, it has only one XDS in it. And then, yeah, that's the only problem. Displays. Cool. Then if I look in that single XDS, you can see all my data variables. I've got my data there. And now something I've done, oh no, yeah. So all my data variables. And then here I'm just setting the gridding parameters, how big I want the image and the cell size. Here I'm doing the direction rotation. So because I'm doing a mosaic, I want a certain phase center. I specify that, and the UVW as well as the visibilities are changed accordingly so that I have the correct phase center. Again, this is not doing any compute. This is just building the graph. Then we make the imaging weights. Okay. Okay, and here we're making the gridding convolution function. So we've implemented a very simple airy disk function to model the primary beams of the ALMA telescope. So we can correct for that. And then here we just basically make the primary beam, make the PSF. And when you call, for example, so there are 2 ways of actually triggering the compute. You can either go dask.compute and put the image XDS into it, or you can call a write, which I've done here. So by doing write image, that's when the compute is triggered, does all of that, and then it produces a image. And then here, we're just comparing the primary beams, the mosaic primary beams that are produced by both NGCASA and CNGI for a couple of different channels, and you can compare them and they're very similar. And then just in the last example, you can see how CASA and CNGI produce basically the same point source simulated image. Cool. Yeah, and then so basically all of our imaging notebooks, that's what we, where we have comparisons with CASA to make sure that the numerics are correct. Here's another example using the ALMA mosaicing tutorial data set of antennae band 7, and you can basically see it's basically the same result. There's less than 1% difference in some of the flux that's being recovered because of slight changes in how the normalization is being done and how we calculate the primary beam, but it's very small. Okay, now benchmarking. This is something that's important to us. You know, why would we change from using CASA to NGCASA if it doesn't perform better? So the big thing to keep in mind is that NGCASA is completely written in Python. It has no C++ in it, except if one of the libraries we're using, has that. But all of the code in the repository is Python. Now, we have 4 ALMA data sets that we are using, plus the big data set to actually stretch NGCASA's legs. So the first 2 are small mosaics. So that's about 30 gigabytes of data that needs to be computed and used and grid and stored. And then we have 2 larger ones at 250 gigabytes. That's for standard grid example, and then another mosaic at 305 gigabytes. And currently we're working on benchmarking a 17 terabyte CHILIS data set. CHILIS is a neutral hydrogen deep field observation. So that has about 17 terabytes worth of data, and we are converting and uploading the viz.zar file. So we will be testing that. We also wrote a Dask performance report scraper. So the Dask performance report is fantastic. The problem is we've got hundreds of performance reports, and we want to pool all of their data and do comparisons and look at different things. So we use beautiful soup and JSON and pandas to basically create a Parquet, a database that's saved to Parquet that has all of the timing information for all of the different functions. So you can see here as example, we have, the amount of time it takes to do the calculation of the ALMA area disk, the aperture grid function, and making of the PSF and so forth. Okay, so first I chose one of the smaller data sets, which is about 20 to 30 gigabytes. And on the left, this is using a single node. Now, what's important is that we're comparing it to CASA. This is the CASA release that will come out soon in the next couple of months, CASA 6.2, which has refactored the way that CASA does parallelism. And to make sure we're comparing apples to apples, we've ensured that the support size of the gridding convolutional kernel that is used by both pieces of software is exactly the same size. So it's doing the same amount of operations. Okay. So the big takeaway here is that CASA and NGCASA has the same performance, which is great. This is a small data set that you can run on your laptop, and we get good performance. So we're literally comparing some Python code that's been optimized to code that's written in Fortran and C++. So we're quite happy with that. And then, of course, the moment you scale out to multiple nodes, the inevitable happens, and you don't get much of a performance increase because there's not enough data and compute to do. But that's to be expected. So the big thing is NGCASA. We wanted to work on a smaller desktop laptop all the way to large clusters. Okay, and as you can notice, how we choose our chunking is quite important to our performance. Using incorrect chunking actually leads to the performance being twice as worse. So we are still trying to develop a heuristic to find a reasonable chunking. But as you can see, there is a range of chunkings that give reasonable performance. Okay, now here, this is the 305 gigabyte mosaic. And here again, you can see that CASA and NGCASA has relatively good performance on a single cluster node. But the moment we start scaling over multiple nodes, we have NGCASA being able to scale out further to give really good performance. Now, the reason CASA struggles is because of how it interacts with data on disk with the table system in CASA core. So with the reading and writing of data where it has to lock and unlock data, which severely stymies it. So yeah, when we were doing the tests, I was literally looking at ganglia, and performance disappeared because it was just trying to read and write from disk, while using ZAR to do our serialization did not have that problem, and we got a good speed up. Cool. Now, oh, yeah. So something interesting, just to show that there is a sweet spot for the chunking here. If you look, the number of chunks, we've got 61 performing the worst, and then the best is 81. So it's not a thing about making your chunks as small as possible or as large as possible. There is a sweet spot for the scheduler to pack things efficiently. Now, this is a graph just to demonstrate it. So on the left, we've got 81 chunks in our for our visibility data, and on the right we have 31 chunks, and you can see the number of tasks that need to be completed. And the Dask scheduler is able to much more efficiently pack all the tasks when it's 81 chunks than 31 chunks. I'm not exactly sure why this is the case, but we've observed this, and especially the question I asked during the break, we would be really interested to try and use the plugin that Landman mentioned to see how that changes how the graph is packed. Okay. And okay, there are a couple of things. I'm almost out of time, but we also ran it on the cloud, and we found that we were able to duplicate the performance we got on our local cluster as well as on the cloud, which is great. And we were able to scale out even further. Again, we most probably want to play around a bit more with the chunking to optimize the cloud. Okay, and this is just showing some of our future plans that we want to do. The big thing is we want to be able to cover all the cases for both the VLA, ALMA, and the NG-VLA, which require doing certain corrections when we do the gridding. So we want to do a W projection, as was mentioned in one of the previous talks, but as well as support asymmetrical beams, heterogeneous pointings, full Mueller imaging, and then modeling our primary beams using Zernike polynomials, which you can see on the right as they rotate with parallactic angle. Okay, and then just the last thing, what's our near-term plans? This summer, we're working on a simulator that includes the full Mueller formulation of the measurement equation. So we want to do that. Our visualization team is working on a CASA GUI desktop that uses the new framework, but will also integrate with CASA. We are looking at a CNGI Carta backend. Again, Carta was mentioned earlier. So we want to see if we can create a backend for Carta that uses viz.zar, well, doesn't use it because it's only for images, but uses image.zar and our new formats. And then a requirements documentation for all of the algorithms that we need and subsystems is being written. And then I guess the big announcement is the NRAO is planning on hosting a workshop on Dask and X-ray this coming fall. And hopefully, if travel is permitted, we can actually all meet together. Thank you.
Thank you, Jan. Yeah, on that note, I'm going to move to our last speaker since we're right on time. There's a few good questions for you in chat. I'd encourage everyone to take that to Slack or maybe at the end if we have time. And our last speaker is John Kenyon. We'll be talking about distributed scheduling problems in radio astronomy, also from the South African Radio Observatory observation.
All right, can everyone see my web browser?
Yes.
Okay, perfect. And can everyone still see my slides?
Yes.
Cool, excellent. This is an exercise in embedding, so anything can and will happen. So yes, as mentioned, I'm Jonathan Kenyon, and I'm going to be talking to you about distributed scheduling problems that we happen to face in radio astronomy, but they're not going to be very specific to radio astronomy. And I'm going to ask everyone to please be a little patient. I'm going to have to give you a few breadcrumbs about astronomy and a few breadcrumbs about Dask, and try to keep everyone sort of on the same page. This is going to get a bit technical. That's because it's the technical problems that I've been trying to solve. But there is a bit of a payoff at the end, so stick around and maybe you'll see it. So fortunately, a bunch of people have already spoken about this in the session, so I'm not going to have to labor this point too hard. So what does our data look like in radio interferometry? Well, we have a standard measurement set, and that is backed by these a columnar storage engine, which is these cast tables. These are not very complicated. They just consist of numbered rows and labeled columns. The only thing that sort of sets them apart from perhaps more conventional databases is that the entries of those columns can be n-dimensional arrays, and this sort of has some repercussions later on. Typically, as you've already seen, the row dimension is millions or larger, channel is several thousand to tens of thousands, and correlations is between 1 and 4. So for the rest of this, I will probably not talk about correlation at all, as they're so small, they're not particularly interesting. The one thing I do want to point out is there's a bit of a devil lurking in the details here, which is that the row dimension encodes both time and baseline information. So baselines are just unique pairs of antennas in our arrays. So it just means that when we're using that row axis, we have to be a little bit careful about how we chunk it and how we do parallelism, as this sort of data needs to stay together to some extent. So the missing link in all this, so how do we get to Dask? That's Dask MS. So this is a Python package written by Simon Perkins, who is here. And what this does is this takes our measurement set format data and exposes it as Dask arrays couched in X-array data sets. Now, this is incredibly convenient, and it takes most of the pain out of expressing our algorithms in a Dask-like way, because we can get our data in this sort of lazy Dask format. And of course, we get all the cool things that come along with X-array, many of which Jan-Willem has already spoken to you about. So I'm not going to labor this point. So in my particular example, the algorithm I'm interested in implementing is calibration. So this is a relatively, the way I do calibration in general is relatively simple, and we'll get into why that's important in a moment. Calibration in general, though, is the process by which we correct a measurement or system so that we can ensure the best data is coming out. And in my particular case, and for radio interferometry specifically, it boils down to determining the complex valued antenna gains. So for those of you who are not radio astronomers, on the bottom left, we have an image of that is subject to calibration error. So this is not being calibrated. Whereas on the right-hand side, we see an image post-calibration. So much of our interesting science, many of our sources are hidden behind these calibration errors. So at this point, I have to sort of like change gear a little bit just to explain the context for this, which is I'm implementing a software package called Cortical. It's the successor to an already existing Python package called Cubicle, which implements calibration for radio interferometers. And the change between this and Cubicle is that this is now going to be an embarrassingly parallel and distributed implementation using Number and Dask. So just to briefly take you through those technologies again. So I've mentioned Dask, MS, and X-array. So that's going to serve to ingest our measurement set data as chunked Dask arrays, which are of course stored in those X-array data sets. And then we use Dask to build task graphs expressing our calibration as this massively parallel problem over those Dask array chunks. And then finally, our sort of workhorse functions are all optimized using Number. So those are just compiled. So I don't want to go into too much detail of how we do calibration, just because I don't think that's going to be useful for this audience. But what I do want to draw your attention to is just sort of the components of calibration, because this will become relevant when I start showing you some Dask graphs a little later on. So what it boils down to is that we're going to have some measurement set inputs. So those are our inputs from disk usually. We can optionally have a predict component. So what that is that's going to be something like a model that we're generating on the fly in memory. So we're not always going to use that. Sometimes we're going to use input solely from disk, but the predict is something that I'm definitely going to show you. Those get fed into these solvers. Those solvers then ultimately produce gains, which are the quantities we're looking for that were mentioned by Lexy and Hertzog. and also some measurement set output. So we're going to do some transformations on our data and then write that back to our data sets. So the thing that's important here is the way that calibration is implemented inside Cortical and its predecessor Cubicle, we can do these operations completely independently per row channel chunk of data. Now that's pretty cool because that's how we get our massively parallel behavior, because we don't expect much communication. But of course, as usual, the devil's in the details, and we're going to get to that as this talk goes on. So finally, before I start showing you some more interesting things, I just want to introduce a couple of Dask concepts. So many of you will be familiar with these, but just for anyone who isn't. So ordering refers to the process of deciding when you have a task graph, in what order the tasks of that graph get executed. So the way that Dask does this is essentially by assigning each task a priority, and then those priorities just inform how the order in which those tasks get processed. And this is distinct, but very much a component of scheduling. And scheduling is about how work gets assigned to workers or resources. So that's if you have a cluster, you know which task ends up where. Okay, so at this point, I'm going to leave my slides, and hopefully this will all work perfectly, and you'll be seeing my IPython notebook again. So the first concept I want to introduce, sorry, I should have said, so these are some common design patterns that emerge in radio astronomy applications, but realistically, these are probably going to emerge in many applications, irrespective of what you're doing. So the first thing I want to introduce is this concept of a linear chain. So here I have a very contrived example where I'm essentially just creating dummy data. It's not meaningful in any way, and I'm doing a no-op. But I'm creating this chunked row channel data. You can see it here. There's a representation. It's just 10,000 rows, 64 channels, and I've decided to arbitrarily chunk it into 5,000 rows and 32 channels. So you can see I've just got 4 chunks. I'm trying to keep this as simple as possible so that we can kind of have some intuition about the results I'm going to show you. And what I want to show you is that if we map these chunks through blockwise, what we see is that we are left with these linearly independent chains. So that is, we've got a graph that's got multiple components, but it can be broken down into subgraphs that do not depend on each other. Now that's important because, first of all, it minimizes communication. It means that we don't expect one graph to need any inputs or outputs from an adjacent graph. And also we expect that when we have to order this, it can be done very easily, because obviously as humans, we can look at this and order it by eye. So if we look at this, we can see that Dask does something very similar, very sensible here. If you are not familiar with these kinds of plots, what they are is essentially each circular node here is a task in Dask. These square nodes refer to chunks. So this is saying, for instance, this is the 0, 0 chunk, so 0 in row, 0 in channel. You could propagate that through. And then this algorithm task is just another task. And then again, there's more chunking information. And then for the ordering, you can associate color like a heat map. So each color, so the color is associated with the priority of each task. And you can kind of use that color to distinguish what's being done first and what's being done last. So in this example, red is done first and yellow is done last. And we can see that Dask is doing something very sensible. It's, it's just picking one chain, going through it, picking the next, going through it. That's exactly what we'd expect. This is all very sensible. But I must point out that this is a very contrived and simple example, and I'm going to build towards something which hopefully you will all appreciate. So this is a real-world example using Cortical. So what I want to demonstrate here is that this is the same pattern. The chains are no longer entirely linear, but they are still independent. So again, we have these independent subgraphs which do not need to communicate. And as you can see, this pattern emerges in an actual application. And you can see that once again, the ordering seems quite sensible. Each one of these is essentially associated with a separate color, which is what we'd expect. We expect to do each one after the other. So the next thing to introduce is is the next degree of complexity. So now, once you move away from these sort of independent subgraphs and start considering the case where you have a shared root node. So what do I mean by a shared root node? It's some dependency on which many chunks depend. So here again, I've got a very contrived example. None of these are doing any work. The point here is not to look at the functions that are being called. It's to look at the structure of the graph that is being produced. So I'm sorry to all the Dask experts in the audience who know all of this kind of stuff. I'm trying to tell a story here, and hopefully the payoff will be worth it. Here, the example's a little contrived because I want to show you something later. So what I'm doing is I'm creating 4 Dask arrays, And all of those arrays are used inside this blockwise operation with a channel array that there's just one of. So if we look at the visualized graph, we can see that we've got these 4 arrays. These I've labeled them row chan here. So this is just to be kind of consistent with the data we use in astronomy. And then we have one array that only has a channel dimension, and it gets broadcast essentially into all these algorithm tasks. Now, we're going to look at the ordering, and you're going to see that it's going to look fine. But this is just something to bear in mind, is that this can put pressure on ordering, because once you have these shared nodes, it becomes increasingly difficult to tell which task to do next. So if we look here, you can see this is again quite sensible. It's doing one of the row chan tasks, then the chan task, and then sort of moving through what remains. So just bear this in mind, we'll come back to it. And then the final pattern I want to show you is the reduction pattern. So all of these occur very naturally in Dask. Dask has mechanisms for doing these. And I just kind of want to show you and guide you through them so that if you see these in your task graphs, you have an idea of what's going on. So here I am just taking, again, an array of 10,000 rows, 64 channels. Here I've not chunked it on channel. I've only chunked it in row, but I've chunked it into chunks of 2,500 rows. There's a reason for that. It's just so that we can see more things a little more clearly in our graph. And hopefully everyone can follow this, is that every row chan chunk gets mapped into a sum chunk function. That's the first component of the reduction. So what that will do is it will take a chunk of input data, and in this instance, it's just calling a numpy sum. It will reduce that chunk of data to a scalar value. It's going to do that for every input chunk. So at this point, sum chunk produces 4 scalars, essentially. Then those scalars are combined in these sum of sums nodes. You can see that's done twice here in parallel. And then finally, those 2 scalars that are produced by sum of sums get put into the sum final, and you get a scalar value out. So now intuitively, we can begin to understand that ordering this is going to be increasingly difficult. Why? Because we have a single output, but we have many inputs. So doing things in an intelligent way gets increasingly difficult. In this example, of course, it's simple. Dask is going to do the correct thing, which is that it's going to choose one branch of this reduction. It's going to follow it as far as it can, move on to the next, follow it as far as it can, and then sort of do that until it's managed to process the entire graph. So at this point, we haven't seen anything that should have blown our minds, but hopefully I'm beginning to build a bit of a picture here. So again, I'd like to show you a real world example of a parallel reduction. So this is the predict component I mentioned earlier of cortical. The parallel reduction lives sort of in this layer. If you look very closely, do not attempt to read the node labels. That's not the intention here. This is sort of just about the characteristics of the graph. You'll see that we have these nodes that sort of combine and eventually reduce down to 1, very consistent with our parallel reduction. However, I introduced the concept of shared roots because you can see that we definitely have shared roots in this graph. And if you look closer, you can see that whenever you have a very dense area of these graphs, you tend to have a problem. Not a problem per se, but you have a node that's going to many, many places. And I'll get on to what we can do about that a bit later. And if we look at the ordering, it looks okay, but it's less obvious that this is correct. And I say that because although our outputs look like they're differently colored, which is kind of what we'd anticipate for good ordering, it's a little less clear what's going on in this layer of the graph. And that can lead to issues. I'll get onto what those issues are in just a second. So finally, I'm going to show you some dashboards. Hopefully everyone here is familiar with the dashboard outputs. So for those of you who aren't, color here is essentially corresponding to the type of task that's being executed. So if you see blocks with vastly different colors, it's likely that they're different tasks. Similar colors tend to be similar tasks. In this example, I'm running on a local cluster, running just one worker with 6 threads. The reason for this is because I do not want to get into the scheduling discussion until a bit later. Now, on the surface, this looks fine. And it's actually interesting that I noticed this kind of pattern in one of Jan-Willem's slides. But there is actually a problem in this output. And that problem is, if you look, you will see that all of these green blocks are clustered on the right-hand side. The way you can think about this is that if these dark green blocks, which correspond to the predict operation, are a producer, these green colored blocks, which correspond to the solver, are a consumer. So the issue with having all of these solver blocks on the right-hand side is that there's no way prior to those solvers being run to alleviate the memory pressure. So we have this predict operation that's going on. It's churning more and more data into memory, But because we aren't running our solver tasks promptly, that data is just sitting, being unprocessed. And that's an issue. That's going to cause out of memory, particularly at scale. Obviously here, this is a very contrived and small example, so we don't have that issue. We can run to completion even though more things are being held in memory than should be. So how do we deal with this? Well, first of all, I'm going to make a point, hopefully, about what I think is the most important takeaway from this presentation, which is, as developers, we are somewhat encouraged to assume that Dask will figure out optimal graph ordering regardless of the complexity of our graph, and also that Dask will always assign tasks to resources in an optimal way which minimizes data transfers. This is not always the case, and I must stress that this is not a disparaging remark about Dask. Dask is awesome, and most of the time it does do the right thing. Unfortunately, as we design more complicated applications, this ceases to be the case, and I think it's very important that we acknowledge this. Okay, so Dask does provide us with the tools to deal with some of these problems. So there are methods for graph manipulation, so altering the graph in subtle ways so that we can perhaps influence ordering. So the example I'm going to show you is specifically here, it's cloning. Inlining also exists. It was mentioned in the Hacking Dask workshop, so I'm not going to go into that. But what it boils down to is that inexpensive but highly connected or shared nodes are often worth recomputing. So this isn't always going to be the case. Some shared nodes are going to be too expensive to simply recompute, but often for radio astronomy applications, the things that end up being shared, so for instance, an array of channel frequencies, they're so much smaller than the data we're processing that simply loading them multiple times from disk is infinitely better than passing them around. To use these graph manipulations functions, unfortunately, we have to be a little bit more involved with our graphs. So we can't just sort of fire and forget. We need to visualize and we need to see what's going on. So here, and I'm going to quickly jump back to, this was the shared root example. So just fix this graph in your mind, because now we're going to look at something else. This is exactly the same code. I have changed exactly one line. I'm going to highlight it here. So all I've done is I've wrapped the chan array in a clone operation. And all that does is it says, Dask, go create a unique copy of this task every time this blockwise is called. And what that means is those tasks produce the same results, but Dask doesn't see them as the same thing anymore. So in this case, chan array is going to be generated here. It's just an array of zeros, but it's going to be generated separately for each blockwise call. And we can see the impact that has on the graph. It's very clear. Now, instead of having that chan node shared across our different arrays, we now go back to having these sort of independent subgraphs, which is great. Because again, ordering becomes simpler and it becomes more obvious what's going on. Again, I'm going to backtrack to my real world example. You will recall I showed you this. This is the predict inside cortical. You can see it's a bit of a mess. However, if we apply cloning in a judicious fashion, we can go back to this case. And again, you can see that this has become a lot more obvious. We don't have that horrible communication, and we get these beautiful independent subgraphs, which are, again, now we can tell that the ordering is kind of doing something sensible because each one is colored differently. So now returning to my previous dashboard, what we see is that we no longer have these solver wrappers clustered on the right-hand side. They're instead kind of being run as our predicts complete. And so we now actually have a way for that memory pressure to be released. And this means that we're going to be less likely to run out of memory and bring our cluster down. So as I mentioned earlier, I've at this point been using a single worker with multiple threads to avoid discussing scheduling. But now I want to move on to that discussion, which is, okay, so now I'm using a local cluster with 6 workers, each running a single thread. The reason for this is just for these little examples, I didn't want to run on a larger system, but you can think of this as essentially being equivalent to running on 6 nodes in a proper cluster environment. What you should immediately notice is we now have these red bars all over our task stream. And the reason for that is because they're transfers. Now, in this case, these red blocks, while they are everywhere, they are not dominating the computation. They aren't a particular problem. However, this is a very small example. So we're transferring very small things. And also it's on a local cluster. So we don't expect things to be bottlenecked by the network. So the point I'm trying to make here is that Dask scheduling doesn't always minimize data transfers. And I say that because we know that we've expressed this as these linearly independent subgraphs, So it's surprising. We know that each chunk of data can be processed without talking to any other, and yet we still have transfers. For transfers may become prohibitively expensive once we reach the situation where we've got large chunks of data, or we've got more cluster workers competing, or indeed if we've got more GIL obtaining code. This one's a bit subtle, and this is, I would appreciate if someone more in the know than me has a comment about this, is that my suspicion is that the transfers in some way invoke the GIL. And so if we have competing GIL obtaining code throughout our computation, things can get very bottlenecked and we get poor performance. I should again point out that Dask does have the machinery to allocate tasks to specific workers, but it, in my experience, becomes very tedious and difficult for large and complicated graphs, which is what we're dealing with here. So what I have done is I have designed an auto-restricting scheduler plugin. So this is a proof of concept. It's not sort of feature complete at this point. Dask allows us to implement these user-defined scheduler plugins, which allow developers to influence and control task scheduling by responding to events in the scheduler. And what this does is it automatically restricts tasks to specific workers. It's non-invasive and it's fairly generic. So what I mean by that is that it doesn't need to know very much about your graph. The way this is invoked inside Cortical, just to show you how simple and non-invasive this is essentially it's just imported from scheduling inside Cortical. There's this very boilerplate function to install the plugin, but what it boils down to is you initialize a cluster, you initialize your client, and then you tell the client to install the plugin. And that's pretty cool that it's that simple. And to show you, you know, the proof of the pudding must be in the eating, this is what happens after we apply this scheduler plugin to this problem. And what you'll see is not only have we eliminated transfers, we now also have a much more intuitive behavior between our workers, which is that each worker is now doing its predict and then the solve that corresponds to that predict. And this means we kind of have a very obvious pattern to look for in our task stream. And that to me is really, really cool. So just to show you that this isn't just a theoretical thing that I can apply to these city small scale problems, this is the original driving use case for why I developed the scheduler plugin. This is a calibration run. This is on about 30 gigs of visibility data. It's probably about 100 gigs or so of things that have to be in memory. So this isn't a huge example, but this is run on 4 nodes at the Center for High Performance Computing in Cape Town, South Africa. And this was very distressing to me when I first encountered this, which is that this graph is dominated by these transfers and there is a lot of idling. There are workers sitting doing no work. I, to this day, do not have an excellent explanation for this. My best guess is that this is something to do with the GIL and transfers. But if someone else has an alternative insight, I would be absolutely delighted to hear it. But we can apply the plugin to this problem, and I hope that the result is as striking to you as it is to me. We eliminate those transfers and we no longer have all that idling. There's also a performance impact here, which I think I should point out, which is that to run through in this instance took about just over a minute, whereas once the plugin's applied, less than 30 seconds. So that's more than a factor of 2 just by having the scheduler plugin installed. Okay, so just to make one or two final comments before I wrap up, this is sort of a preview. So this is not my work, this is work in progress by Simon. So he's taking this idea of an auto-restricting scheduler plugin and extending it to also attempt to do some intelligent reordering on the fly. And the way he's doing that is by leveraging Dask's annotation system to annotate your data inputs with their chunk IDs. Those chunk IDs can then be propagated through the graph using a breadth-first search, always tie-breaking in favor of the lower value chunk IDs. And then ultimately you could stripe those chunk IDs over your workers, the idea being that then each chunk would kind of be sent to a separate worker. So this is, we've got some early tests of this going, but it's not yet complete. And at that point, I have spoken so fast that I think I'm a little early, but I'll leave you with my conclusions, which is just that Dask is obviously an immensely powerful tool for expressing our radio interferometry and radio astronomy applications. Dask ordering and scheduling often does the right thing, but it doesn't always do the right thing. And as developers, we've got to be quite aware of that. We do have tools to manipulate ordering and scheduling, but they do require a much deeper understanding of task graphs. And then finally, I've implemented this proof of concept scheduler plugin, which certainly for my application massively improves performance and eliminates unnecessary transfers.
Wonderful, thank you. Thank you, Jonathan. We have some time for a few questions, and I'll just read out this last comment. Beautiful task stream, great work on this. And if folks have questions, we have about 4 minutes.
Yes, John, I might have missed it, but what does your plugin actually do in terms of what heuristic does it use to decide what tasks to restrict to what workers?
Yeah, so that's the some caveat. I was kind of leaving it for a question because I was nervous about going into too much detail. So it's doing something rather simplistic at this point. So what it does is it identifies all the terminal nodes in your graph, and it identifies all the root nodes in your graph. So terminal nodes are nodes that have no dependence, and root nodes have no dependencies. And then what it does is it tries to figure out for every terminal node, what are its associated root nodes? And it tries to then split up the problem in that way. So if you have terminal nodes that share root nodes, it will group them together. That the idea being that if terminal nodes share root nodes, we don't want to transfer things, so we allocate them all to a single worker. There, of course, the caveat here is that this doesn't work well for doing something that's just a parallel reduction, for instance, because then you only have one terminal node, but it depends on all input nodes. So I do have ideas of how to do better and how to sort of combat that problem. But for now, for my use case, it's sufficient with what it does, which is that we've kind of got the problem split up sufficiently that by just identifying terminal nodes and root nodes, we can create these unique groupings and then just map those unique groupings over our workers.
Okay, so this is kind of specialized for embarrassingly parallel problems. We have completely independent graphs.
Yeah, so it does kind of have that, but
yeah, it's cool.
It wouldn't have to, if that makes sense. So you could definitely conceive of a way in which you can recognize highly connected nodes and disqualify them from your decision making. So you acknowledge that some nodes you're okay to transfer. Basically, it's just at the moment my plugin always works. It just might not do what you want it to, which is that if it decides that in order to eliminate transfers, it needs to allocate all the work to one node, it will do that. But that's something that obviously can be improved.
All right, thanks.
Any more questions? We have about a minute, either for this one or the previous talk.
Should we talk data formats? Because I think what I'm kind of picking up is that like there are 3 different independent streams of development here. And I'm just wondering, like, if we're all going to end up developing our own formats for our own different reasons, which is valid. But it would be nice for all our software to talk to one another at one point. So I just want to put that out there. Yeah.
I tend to agree. I mean, that's the one advantage that the radio astronomy community had for 20 years is that we basically coalesced around the measurement set. So whatever the next thing is, hopefully it's also, something that we can agree on.
On that note, I am going to have to end this session because there's a new one starting. But yeah, I encourage everyone to take this on Slack. It was great. Thank you so much, everyone.
Okay, see everyone
very
on
much.
Slack. Yeah.
Everyone.
Thank you.